Imagine trying to build a bridge without understanding the difference between a solid beam and a collection of individual bricks. Both are construction materials, but their properties dictate how you use them and what you can build. In engineering, signals are our fundamental building blocks, and understanding their nature is just as crucial. Differentiating between continuous and discrete signals in engineering is absolutely essential because it dictates the mathematical tools we use, the processing techniques we apply, and the hardware we select to interact with the world. This fundamental distinction directly impacts how we accurately model, analyze, and implement systems that handle real-world phenomena. The core reason for this differentiation lies in their very nature and how they representing information. A continuous signal, often called an analog signal, exists at every single instant in time and can take on any value within a given range. Think of the fluctuating voltage from a temperature sensor or the sound waves from a musical instrument. These are smooth, unbroken representations of physical quantities. We analyze these using continuous mathematics, like differential equations and integrals. In contrast, a discrete signal is only defined at specific, separate points in time and typically takes on specific countable values. These signals arise from sampling a continuous signal, converting it into a sequence of numbers, which is the language of digital computers and microprocessors. For these, we use discrete mathematics, such as difference equations and summations. Knowing this difference directly informs your engineering decisions. When dealing with continuous signals, you might design an analog filter using operational amplifiers to remove unwanted frequencies, or use an oscilloscope to visualize its real-time behavior. For discrete signals, you would instead implement a digital filter algorithm on a digital signal processor or microcontroller, processing stored data in steps. This understanding helps you choose the right domain for your analysis, whether it is the time domain or the frequency domain, and select the appropriate mathematical transforms, such as the Fourier transform for continuous signals or the discrete Fourier transform for discrete ones. Failing to recognize the signal type can lead to critical errors, like aliasing, where high-frequency components in a continuous signal are misrepresented as lower frequencies when improperly sampled, distorting your data. This clear distinction is also central to understanding key interface components like analog-to-digital converters, known as a DCS, and digital-to-analog converters, or DACS. An ADC is the bridge that converts real-world continuous signals into discrete digital data that computers can process, while a DAC performs the reverse, transforming digital data back into an analog form. Properly sizing and selecting these components, considering parameters like resolution and sampling rate, is directly tied to the signal type you are working with. This knowledge ensures optimal system performance, efficiency, and cost-effectiveness by matching the processing to the signal's inherent characteristics. Ultimately, recognizing whether you are dealing with a continuous or discrete signal empowers you to build robust and accurate engineering systems. It enables you to choose the correct analytical framework, design appropriate hardware and software, and correctly interpret the behavior of complex systems. This foundational knowledge is not just theoretical. It is a practical necessity for translating the dynamic, continuous physical world into the precise, manageable digital data that drives all modern technology.